Hi, welcome to another video. So this one's talking about, it's for beginners, voltage dividers and analog to digital converters. Right, so this is my 5-inch TFT display. This is the time. This is a time string coming in via Bluetooth. You'll see there. And I've got another Bluetooth up in the corner, just on top of the hard drive there. That Bluetooth was picking up the solar panel charge current. So if you want to know how to convert current to voltage, look at my other videos. I've got an analog device. So that's my solar panel charge current, but I thought, well, while I'm transmitting that string, I wanted to transmit another string via the same Bluetooth. But to keep the string simple, the string length has got to be the same as the first one, otherwise trying to pass the code or trying to decode it or compute it becomes difficult. So what I wanted was the solar panel charging current, which is here, and the solar panel charging voltage or battery voltage, which has just come in here. And it all seems to be working. I had to use a voltage divider because my PIC microcontroller is only 3.3 volts, and as you know, if you exceed something like 5 volts on a PIC, you'll blow it up. So I'm going to show you how to use a voltage divider, that sort of stuff, and go from there. So that's just a refresh memory. That's my microelectronica EasyBig Fusion version 7. I've got two Bluetooth devices, one down there, one up there, picking up this data. As I say, solar panel charge current is disconnected because it's down here at the moment, and solar panel voltage. Right, so what I've got upstairs is this GLCD clock. Right, in case you haven't seen it from the other video, this is my GLCD clock that picks up the time via the MSF transmitter in Anthorn, Cumbria, and this has got an MSF receiver. It's basically just a clock. But while I had the clock upstairs, because I want to data log the solar panel data, I thought, well, I'll connect it to the clock, and now I've got sort of time domain, time format. So let me take you back to the circuit board. Right, this is the back of the clock. This is the simple UART transmitter, Bluetooth, transmitting my data. Just transmitting the time, nothing else, and that's running off my 5-volt PIC microcontroller clock. So I've got two resistors in line with the transmit receive lines, and this board is an additional sort of clock PC, but I'm using it for the solar panel. I've just got simple power there, and in that bottom corner a 3.3 volt regulator with a decoupling capacitor, so that's power and ground. Right, so this wire tells this PIC microcontroller from the clock every sort of 5 or 10 seconds past each minute. This goes high, a pin goes high on here, and this transmits the UART via this second Bluetooth UART transceiver. Transmits that to my microcontroller, which is obviously down here. This obviously normally lives upstairs. This bit here is the analog devices with my current shunt, and that converts the current to voltage. As I said, see the other video. Right, so I've got my analog devices current converter, voltage to current converter, going in on one analog to digital pin, AN0, and I've got this blue wire here going into AN1, so the second analog to digital converter channel. Now that is running to this voltage divider, and you might see, so I've got this 10.8 volt lithium battery in the corner to simulate a higher voltage running into the PIC. I've got that running to this voltage divider, which is actually made up of 6 1K resistors. I could have used a 5K and a 1K, but I haven't got a 5K, so it's got to be equal values, or in this case it does for simplicity. So I've got 6 1K resistors in series, and you'll see, so that's 10.8 volts there, and ground is here. this little blue wire at the back, that's going into the ground on a PIC microcontroller, and this blue wire here is picking up this voltage divider on the last resistor, just the last one before the ground. So I'm picking up there, but what I'll do, I'll show you the drawing on a PC. Before I pull up the drawing, this is the program showing the UART transmission via Bluetooth and how I'm doing it. So let me just go back to the beginning. So it's actually, what processor is it? Microcontroller. So it's a PIC 16F1519 running at 8 megahertz. And you can see I initialize the ADC, but you don't have to, and initialize the UART 9600 baud rate, small delay, choose a 0 and 1 are the ADC inputs. So this is the AND cell select. So AND cell A is a analog select. I want pins 0 and 1 for the analog input, so I've got to turn those on. So if you go to your calculator, view, programmer, and also go down to binary down here. So we want pin 0 and pin 1, so that's 2 ones there. This decimal is a 3 and hex is still a 3. So look, AND cell select, so we've got analog select pins 0 and pin 1 for the AN0 and AN1. Then all the rest are all digital. And then in a while one loop, you can see I'm just calling it solar panel ADC read and battery voltage ADC read. So that's reading of channel 0, reading of channel 1, converting into strings, and transmitting via UART when I get the signal from my clock. So when this bit goes high, 2-second delay, and it transmits that string with the beginning of solar and transmits the solar panel current string. Small delay that ends carriage return a new line, and then 2-second delay, and UART write text power. So I've chosen power instead of voltage because it's got the same number of characters as solar. So transmits the solar current and then the solar panel voltage, and then carriage return new line. So that's the format for sending the simple UART via Bluetooth, and that's it. That's the end of the program. So that's all that microcontroller on the back of the clock is doing. Right, so this, as I say, is for beginners. Most of you will probably already know. This is a simple potential divider, voltage potential divider. So I'm using 3.3 volts because that's what the PIC microcontroller I'm using runs on. So if we've got a 3.3 volt supply, if you get the supply and the ground, and you get 2 resistors of equal value, join them in series and measure the voltage in the middle, you're going to divide that voltage by 2. So it's a potential divider, divides the potential. So in this case 3 volts or 3.3 divided by 2 equals 1.65 volts. So you're dividing that 3.3 by 2. So what I'm doing, using this 3.3 volt supply, running that down to my microcontroller, which is on the back of the clock, and I'm demonstrating in place of my solar panel. Let me see if I can zoom out a bit. Right, I've got my 10.8 volt lithium battery simulating like the position of a solar panel, but my solar panel is only a 50 watt, just for experimental purposes. It's got an output of roughly 20 volts peak, so I can't put 20 volts on a 3.3 volt microcontroller because it will blow it up. Some pins are 5 volt tolerant, but anyway, so for getting the tolerance I can't stick 20 volts into it, so I need a potential divider. So what I've done here to simplify the divider, and for tutorial purposes, I want to get 20 volts down to no more than 3.3. So what I've done, I had some 1K resistors. I thought put 6 of them in series and you're dividing it by like 3.3 roughly. So 6 resistors, tap off this last one. If you start with 20, you end up with 3.07 volts into the ADC pin. So you see I've got a little note there, 6 resistors dividing 20 volts by 6 equals 3.333 volts per resistor. So you can use one 5k and one 1k if you have a 5k, but I didn't have a 5k, hence the 5 1k's and then another 1k at the end. So looking down the bottom there, 20 volts divided by 6,000 ohms equals 0.003 amps or 3 milliamps. If you want to see the voltage and current conversion, got a little note there, see my other video one at a time on this one. So there's my supply, and that's my blue battery, just giving a high voltage in to the PIC micro. Let me move this down. So most analog to digital conversions are carried out using 10-bit analog to digital converter. So 10-bit converter gives you a total of 1023 bits per conversion. So what you do is divide your microcontroller supply, the voltage supply rail, by 1023 to get your reading per bit. And some of you might have spotted my earlier mistakes, so I've just revised this. So my PIC is a 3.3 volt microcontroller. That means for the ADC conversion I need to divide 3.3 volts by 1023. That will give me a value of 0.00322 per bit of the conversion. You might be running a 5 volt microcontroller of some sort, so you need to divide 5 volts by 1023. That will give you 0.005 per bit conversion. Let this clock refresh and see what voltage we've got coming off that battery through that potential divider and through this blue wire. So let's see what it says. So that's a time string, solar panel current, and that's our new string for the voltage. So 548. So it doesn't really mean much at the moment. Let's repeat it again at the top, 548. So we want 0.00322, 0.00322 multiplied by our conversion result, which is 548, equals 1.764 volts. And remember, to get this divided down figure back to the original value, you just multiply it by 6. So if we multiply this by 6 times 6 equals 10.58 volts. So that's the value of my lithium battery. That ADC voltage, let me turn the light on, was measuring, like you saw in the picture, that potential divider voltage divided by 6 times. There we go, 1.767 volts. Well, so this is my interrupt for the Bluetooth, where I'm picking up the 2 strings. So because both strings are the same length, makes it easy. So Bluetooth J is UART read, J++, if J equals 13, J equals 0. As I'm turning on an LED, so I know I've got to this section. Ready equals 1, and I'm clearing the interrupt flag. Now I'll run down to the routine. Well, so if ready equals 1, a string equals, that's a string picking up this solar there, that's what that means. Have a look at the help files if you've not seen the other videos. If string does not equal 0, so this is a result for the first ADC conversion. So ADC, so 1000, 110s, position 8, 9 and 10. That's if there's an odd character or space, just telling it there's a 0. byte to string, and TFT writing the results. So that was for the current, solar panel current, and then the second string I've just added today, that bit there is just writing the value to the EEPROM. You can look at the other video if you're not sure how to do that. Right, so because the strings are the same length, I've called this one string 3, and it's Bluetooth, and this string begins with power, so this is the voltage I'm picking up. So again, if string 3 does not equal 0, ADC, so string 3 position 8, 9 and 10. I've just noticed this bracket's in the wrong place. Byte to string for the 3 ADC values, and then TFT write text, writing the individual bits, and then that's the total. So voltage, ADC, so 1000, so it's times 100, so it's shifting it left 2 places. Then ADC second value and ADC third value. So you can see times 10 times 100, just putting them in the right position. And interstring voltage, and that's the final voltage on the screen. And I'm turning the LED bit off down the bottom. Hopefully this has helped. Thank you very much.